So here's the good news. We've seen vector spaces, right? And we've seen subspaces. And we're going to talk about a couple of important subspaces today. And it's essentially the same crap we've been doing before. And that's good, right? So we're going to, what we're doing right now is we're kind of doing a rehash of what we did with Rn, only we're doing it in slightly more general context. So we went over what a vector space was last time, and that's kind of a long list of, I think I had 9 things on there. Recall, if C is a vector space, and suppose you have any vector space and you pick any collection of vectors inside of V that you want. In fact, this could even be an infinite collection if you like, as long as they all live in V, then this is a subspace. Let's check this. This will be kind of my final example. We did lots and lots of examples of split subspaces last time. Remember, we said functions, continuous functions, differentiable functions, polynomial functions bounded in a certain degree. So there's lots of them out there. But this is kind of a big prototype, right? So if I have any vector space I want, take any collection of vectors out of there, their span will always be a subspace. Let's check that out. Does anybody remember what 3 things does a subset of a vector space have to have going on for it to actually be an honest to goodness subspace? What's one thing? Yeah. Has to have the 0 vector and what else? Yeah. What's in that?
Under addition and scalable.
It has to be closed under addition and scalar multiplication. Y'all remember that? So zero vector is in the subspace. 2, if U and V are in subspace. So it's the sum, so that means closed under addition. 3, if U is in the subspace. So is C for any real number C. And that last one means closed under scalar multiplication. So let's check out span. By the way, what do I mean by span of a bunch of vectors? Do you remember? I'm gonna write this assessment station. This is the yes, go ahead.
I was just gonna say it's like the set of all linear combinations you can make with it.
That's exactly right. It's every stinking linear combination that you could ever make with these vectors. So it's every possibility that you have like this. And you can freely choose those seeds, any seeds you want, as long as they're real number, right? Okay, so let's check our criteria. The first thing we need is we need for the zero vector to actually be in the span. Can I make the zero vector by choosing the constant sagaciously? How can I do so? Yeah, the easiest way is to take them all zero, right? And I'm into easy. So notice if C1, C2, CK are all zero, then we've got the zero vector. Okay, so we've got that. Everybody agree with that? What else do we need? We need to be closed under addition, as you all say, right? So that means if I have two vectors in the span, when I add them up, it's still got to be in the span, right? Well, I guess the best thing I can do is just write down what two vectors look like. If U is in the span, it looks like this. That's what a typical element of a span looks like, right? And let's say B is in the span. Where D's are perhaps different. Now, I'll write it over there on that board. What happens when I add U and B? Basically, I just add these vectors all up, right? And isn't this just everybody agree with that? And what do we have now? We have a brand new linear combination of the B's, right? So this is in span. Correct? And finally, we need to have it closed under scalar multiplication. So if U is equal to C1B1 plus C2B2 plus CKBK, and let's say A is a real number. If you look at AU, this is AC1 B1 plus AC2 B2 plus ACK B. This is one of the easiest ways to build your own subset of a vector space, right? Kind of a build your own. Just take any collection of vectors, and this is sometimes called the vector subspace generated by these vectors or the span of these vectors. Just take all possible linear combinations. So for example, imagine three vectors, right? Imagine the space in which we live, right? Every point in space that we encounter can be described by a three vector, right? If I set the origins. Right? What if I have two random vectors? Two random three vectors in free space. They will generate a subspace. Anybody describe what it's going to look like? What's that? Everything. Can you get everything in all space with only two vectors? Right, but what happens if they're not co-linear? Right. So, what if they're not? Actually, you sort of actually isolated a couple of important points. What happens if the two vectors are collinear? What's the subspace going to look like? Well, if they're both on the same line, so if the two vectors look like this, here's one, and here's the other one. What's that going to look like? A line. And if they're not collinear, it'll look like R2, right? So it'll look like a plane, right? You're going to have at least three. If I give you three vectors, does that necessarily going to be all of R three? Maybe not. What could go wrong? I could have two vectors that are not collinear, so they sit in a plane, and then my third vector might accidentally be in that same plane, so you don't get everything. Right? The three vectors are necessary, right? You got to have at least one. Okay. Any questions? Okay, so here's an old friend, actually. This is something that we've seen before, in a more specific case of RN. Well, actually, definitely. Null A is the set let me point out, this is sometimes called recurrent. So if you hear that word, somebody asked me that word in a review session for the last exam, we didn't use it yet. Well, now I've used this. Kernel, this is called kernel of linear transformation. T from Rn to Rm, defined by Tx. Basically, what it means to be kernel is it's all the stuff in Rn that T sends to zero. Let me point out that this here, A is in R by N. Then the null of A is in substance. Now I'm going to generalize this a little bit later today. I'm going to generalize this. Null space. Okay, so right. So let me actually let's verify this. Okay, I'm gonna go through and I'm gonna try to convince you that we've got the big three here for subspace. That is to say, the zero vector is in null A. That you have two vectors in null A, the sum is in null A, and then a scalar multiple when you think of null A. So So that's the zero vector, and I emphasize it's in Rn, right? Because it's the n-dimensional zero vector. Well, and what happens when you multiply any matrix times the zero vector? What do you get? Of course, this zero vector is actually in Rm. Right, so first zero vector has n rows, and the second one has n rows. So we establish the first bit. The zero vector is actually in the null space right, because A times zero is supposed to go. Suppose now that U and V are in null A. Let's see what that means. This means that AU is the zero vector, and it means that AB is the zero, right? Am I okay? Now, what we need to do is we need to show that U plus V is still in. Let's see what happens. Let's check U plus V, see if it's still in null space. What do you suppose my next move is going to be here? I multiply U plus V times A. What's that equal to?
Just distribute it times 3 plus.
Agree. Why don't we just distribute this out and see what good Lord takes us? Well, what are these for? And I don't know much, but I do know if I add the zero vector to itself, I get zero vector. So how about that? So it's closed under addition. And finally, suppose U is in null A. And what does this mean? It means again, AU is zero vector. Now let's check a constant. Let's see if a constant times U is still in the null space. So I've got A times CU. What can I do? I can pull the C out, correct? And I don't know much because AU is zero, right? So this means that the null space of A is actually a subspace of R. Everybody okay with it? Any questions on it? All right. Let me do a concrete example. Now, also, since we've talked about this before, let's see if we can find a basis for it. Can anybody, by the way, can anybody remind me what a basis is for a subspace?
It's like, kind of like the minimum number of vectors you can describe the subspace.
You're technically right about that. Let me give something that's probably. So what it is, you're right, it is minimal. So what a basis is it is a spanning set, right, of the subspace, right? So everything in there is a linear combination of that. And it's got one other property that's guaranteed by your minimum. Anybody remember what the other thing is? Yeah. Good, very good, linearly independent. Let's see if we can dig a basis out of this, which is kind of those ways too. And I set this up, by the way, let me show you guys a trick. So you don't have to do this, and in fact, if you've got like a computer or something, you might not bother doing it. I'll show you kind of computation. What's the first thing I'm going to do probably with this when I reduce this matrix? I'm probably going to use that because would everybody agree the leftmost column is going to be a pivot column, right? But it's really obnoxious, isn't it, right? Because nobody wants to divide by 2 or by 3, right? Because how annoying is that? Well, actually, you can use something called the Euclidean algorithm, the integers, but that doesn't matter. I'm going to take an intermediate step first. So this is kind of something of mathematical interest, which you don't really need to know get under the hood with it, but you can always use it. If you have 2 integers that are relatively prime, there's always a linear combination of those integers that gives you 1, right? And 2 and 3 don't have an element prime. So here's what I'm going to do, just to make further work easier. I'm going to add -1. I'm going to take -1 times this plus this. So that doesn't go down to 0, but it does give me this. 1 minus 1, 2 minus 2, 1. Right? And now I've got a 1 there. I'll do the same thing here. 1, -1 times this plus this. 2, 0, 1. Now I had to take an extra step to do that, but now I don't have to deal with 2/3 or anything stupid like that, right? So now I'm going to take this top row and I'm just going to use this 1 to eliminate the stuff below it. And it's 0, see, multiply by -2 and add, I'm taking 2 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 and add. Oh, okay, very nice. And I'm going to multiply this by -1 and add it here. 0, 5, 0, 2, 0. Now, again, I have to divide by 2 or 5. I'm going to do my same trick again, but I'm going to key on this one. So 1 minus 1, 2 minus 2, 1. And of course, by the way, if you decided to, in this first step, divide by 3 and 2, that's great too. It's just I never have to work with fractions. I'm going to multiply this 0 minus 2, 0 plus 1, 0. I'm going to multiply this by -2 and add it here. Oh. And now I have totally vanquished this matrix for sure, right? Because what can I do now with this bottom row? What makes this easier? Right. Everything's 0 except for this, right? So I can totally kill these things here. So this is 0, 1, 0, 0, 0. And it just killed everything above it. 0, 0, 0, minus 1, 0, and 1, 0, 2, minus 2, 1. And now what? Well, now I've got another row that's only got a, well, in this case, -1. By the way, I'll switch this to positive. Is everybody okay with that? Just multiplying that by -1. Now I can just take this out. Right? And so this is going to be 1, 0, 2, 0, 1. And I'll swap out people. And that looks like a relatively special point. Okay, let's take a look at this. I've got 5 columns in this matrix. How many of these correspond to 3 variables? 2 of them, right? Which ones? The third of the 5. These correspond to 3 variables, and these other ones are basic. So I get x3 and x5 are 3. I get a couple of easy equations too. What else do I get? What's the total rip-off here?
X2 equals X2 and X3. So I guess principles.
Well, actually, let's see. So I should be able to write the basic variables in terms of 3 variables, right? What is x2? That's 0. Right? This equation right here is just x2 is 0. Right? What's x4? Also 0. The only one really with any meat on it is this one right here. The first equation says x1 can also be written in terms of the basic variables. This top equation says x1 plus 0x2 plus 2x3 plus 0x4 plus x5 is equal to 0. But remember, these correspond to, this is a homogeneous solution. These all correspond to 0. This equation is x2 equals 0, x4 equals 0. Nice, right? So if I put this together, well, let's see what we got going on here. Well, x5 and x3, they're free. So all you got to do, you just got to put those in there. X2 and x4 are both 0. And x1 should be minus 2x3 minus x5. Agree? So this is x3 times -2, 0, 1, 0, 0. x5 times -1, 0, 0, 0, 1. Gotta do that. By the way, I know you guys know this because I asked you a question like this in the first exam. However, now I'm going to pick it apart a little bit more. And instead of just repeating it, I'm going to see what's true. So it's like telling you this basis for no way. Yeah. Just these 2 vectors that are multiplying the 3 parameters x3 and x5. So -2, 0, 1, 0, 0. And -1, 0, 0, 0, 1. Now, if I remember right, a basis has to do 2 things. It has to span and be linearly independent. The reason this spans is from our earlier theory on homogeneous equations. Every solution to that homogeneous problem is something times this vector, something times that vector. So it spans. Can somebody tell me why these 2 have to be linearly independent? These null vectors always come out of form. So let's suppose that x3 to 0, 1, 0, 0 plus x5 minus 1, 0, 0, 0, 1 is equal to the 0 factor. For these two vectors to be linearly independent, what conclusion must I come to about x3 and x4? If these two are linearly independent, if minus 2, 0, 1, 0, 0, and minus 1, 0, 0, 0, 1, if those two are linearly independent and you have a linear combination being the zero vector, what must be true about x3 and x5? They both have to be zero, right? And actually, in this case, it's not too difficult because here's, you can put this back sort of in the original form here, minus 2x3 minus x5, 0, x3, 0, x5, right? Now, if this is a zero vector, these two have to match, which means that x3 is 0. And if it's a zero vector, then these two have to match. So x5 is 0, and bang, you're done. It's linear. Now, this is always the way that we get the basis for the null space, is to solve the homogeneous equations. And the three parameters are basically the multipliers, and the vectors that multiply are your linearly independent basis. Yes.
So are x3 and x5 not free, like that have to be 0?
They have to be 0 if that linear combination adds up to 0. Right? But this linear combination could add up to many things. I mean, you could take just pick 5 random numbers in here, and you can actually solve this linear. If you pick 5 random numbers where the vector is actually in null space, then you can solve it. Right? So, for example, you could take this to be 1 and x5 to be 7, right? And that will give you this vector here. Whatever I get with 1 and 7 for them. So that's going to be minus 9, 0, 1, 0, 7. This is a vector that's actually in the null space. Right? So if you take that vector and you multiply it, if you take A times that original vector, you should get the 0. Okay. But if you have a linear combination, this is 0 vector, then this is 0, 0. But let me tell you something else about this. How did I get this vector in null space? By choosing this to be 1 and this to be 7. Because that's a basis, that's the only way I can choose x3 and x5 to give you this vector. Yes.
Did you set it equal to the 0 vector because it's just easy to work with?
What I said it equal to the 0 vector to show that those two things are linearly independent. Right? Because that what I was trying to do is justify that those two things are a basis. Right? I already know they span it, but I needed there also to be linearly independent. Okay. Everybody okay? All right. That's actually one of the things about basis, and we're gonna rehash this later. But if you have a basis, everything in that space is a unique linear combination. Okay? So, for example, if you look at this spans the 7 vectors. But this is not a basis because there's too much in it, right? This is not a linearly independent set. And for example, notice that 3, 3 is equal to 1, 1, 1, plus 1, 2, 2. Anybody see another way of doing it? Yeah. Sure, why not? Right. Or -3 times 1 plus 3 times 2 2. In fact, there are infinitely many different ways to write 3 3 as a linear combination because they are linearly dependent. Yes.
So is the premise sort of that like, I'm doing it for linear. If it's linearly dependent, what the fact is like linear combination, the other ones, and then isn't it expanding?
Yeah, that's right. So what will happen if you have a linearly dependent set? When you look at what spans that, you will get a subspace, but your set of vectors expanded is it's not economical enough. And it turns out that given any vector in that space, will be infinitely many ways to write it. When it's linearly independent, you get a unique representation. And often that's very important when you're doing math problems. Because, for example, I'll give you kind of an example of the old days. Do you all remember back in Algebra 2 in high school, what did you do with quadratic equations, right? Oftentimes you get these quadratic equations that you knew that they were the solution to some word problem, right? And then you got two solutions, you got -1 and 7. And then you had to make a value judgment on which solution to pick, right? You had to look at the problem and figure out, okay, which answer makes sense. Is it the -1 or the 7 that makes sense? Right? This is why unique solutions are very nice because the solution is just there and you don't have to do any further calculation. Okay, other questions? Okay, another thing that we can look at, of course, is definition. If A and R in by then, and let's say, let me write out this way. I want to write A in terms of its column vectors. Then the column space then is the span of the columns. Column vector, that's all. Right. So let me make the observation first that each A1, A2, A10, then R. Right, because remember, my original matrix A has m rows, so the column vectors are all m high, it's number of rows. So column A is the subspace. It's clearly contained in Rn because every one of the column vectors is in Rn, right? Why is it a subspace? Because we've already shown that the span of any collection of vectors is a subspace. So since the column space is the span of this, it has to be a subspace of Rn. Let me point out that note column space A is the same thing as the set of vectors B and Rn, such that B is equal to AX. Some vector X in or in. Because notice that each B is actually a sum of the columns of A. So if B equals AX, then B is in the column space and conversely. So column of A, column space of A is all of RM. If and only if AX equals B has a solution for all B in now, let's do that example again. Let's revisit this original matrix here. We had 3 minus 5 6 minus 7 3 2 minus 4 4 minus 5 2 and 3 6 minus 5 3. By the way, somebody remind me, what was the dimension of null space? It was 2, right? Because remember we had 2 linearly independent vectors in that solution, right? Let's see what the dimension of column space is. So let's produce this as before. So you do the same reduction and you get same matrix. Assuming I did it right the first time. And I think the matrix we got was now, what are the pivot columns? The pivot columns are these, right? So a basis for column A you are correct, but I'm going to do something else anyway. They have to be pivot columns from the original matrix. What was the other one? Y'all remember that? How we had to go back to the original one? Well, let's see what we get. 3, 2, 3. Minus 5 minus 4 0. And so, by the way, look how flippant I was, flipping the signs. Can somebody explain why I can do that? Right, I let the first one alone, but I just said, oh, I don't want to buy a sign, and I changed the sign a little. Can somebody explain why that is kosher? Yeah.
Because if you were making a linear combination, instead of multiplying it by like -3, you just multiply.
That is correct. So you could actually replace you could replace any of these columns by scaling multiple columns, as long as that scale is not zero. Right? This is the basis of column A. Right? The column space of A is a subset of R3, right? And you can check, in fact, it might be a good exercise to check this is linearly independent. These always, the row relations that you do preserve linear independence, and this always be a linearly independent set. However, what you said in this particular case happens to be true. This is also a basis, right? This does not always work. You need to go back to the original matrix, right? But can somebody explain why in this particular case it works? This is a subspace of what? Right, the column space. I'll call it a column. So everything going on in here, every linear combination is inside R3, right? Can somebody tell me why this has to be all of R3? That's right. You have 3 linearly independent vectors. So it has to be all of R3. We're going to be more precise about that later. That's absolutely right. You got 3 of them and it's R3, 3 linearly independent, which means in this particular case, you could have used these 3. However, be careful, always go back to the original. Any questions? Okay. Let me give you one last definition example. Let E W function T W is a linear transformation if T of U plus B, T of U plus B of U, for all U, B, and C, and 2, P of C B, C T of B, for all B and B, C. Now, let me give you a couple examples. We'll talk more about this next time as well. Let me give you a couple of linear transformations here, and you should check that this works. C is the collection of continuous functions whose domain is just the interval from 0 to 1 and whose range is the real numbers. Right? I shouldn't say range, target is the real number. Right? We've seen that this is vector space. Let me give you a couple of linear transformations. Let's go function T. T goes from C into R. T. Okay, my input, my vector is a continuous function, right? My input is a function, my output is a real number. So I'm going from C to R. Check that that's a linear transformation. So the number output is just integrate that function from 0 to 1. 2. Let S from C to C. S of the function f is the integral from 0 to x of f of t to t. Check if that's a linear transformation. By the way, good luck writing these as matrices, because continuous functions do have bases in vector space, but actually they have infinitely many elements, right? You might check that when you go from differentiable functions to differentiable functions, the derivative is a linear transformation as well. So there's a lot of these old friends from calculus that show their heads again. Okay, any questions? All right, put this in your pipe and smoke, and we'll talk more about this next time. If you're going to see me, if you're going to see me outside of 11 and 2, you can see me now.